Okay. So today I will, instead of the whiteboard, I will actually use this presentation, which was prepared by Uğur Hoca, Uğur Karban, when he was employed at Northern Cyprus campus. So he he gave us his presentations used in the aerodynamics class there, and I'm going to use his slides. Anyway, we have already discussed this yesterday regarding how we actually treat oblique shock waves. So basically, just to summarize, basically we decompose, what we do is we decompose the velocity vector into a normal component that is normal to the shock wave, so perpendicular to the shock wave, and a tangential component of the velocity vector to the shock wave. And we apply basically all the normal shock wave relations, normal shock jump relations across the oblique shock wave. And the input Mach number is, instead of using M1, we use the normal component of M1. And so we just apply normal shock wave relations to find, for example, the static pressure jump, the static temperature jump, the density jump across an oblique shock wave. Regarding the Mach number, after the shock wave, it requires, and also the Mach number after the shock wave, and also the shock wave angle is an unknown. So the given values are, as I tried to describe yesterday, are the deflection angle theta here in the slide. This one is given. This one is the input Mach number that is given. Beta is unknown. Once beta is known, then we can actually calculate the normal component value at inlet N1, and then we can therefore apply normal shock wave relation to find N2. And then if we know theta and beta, we can actually calculate M2. Now, we did that yesterday, and we arrived at this equation, the theta, the well-known theta beta M relation. This theta beta M relation is this equation, and also, as we discussed yesterday, the left-hand side of this equation, the theta value is an input. This is the deflection angle of the ramp into the supersonic flow, or if it's a wedge, if it's the half wedge angle. So this is an input, and one is an input, so this is an input. The unknown is beta here, but it's quite difficult to isolate beta to the left-hand side of this equation. So generally, in aerodynamics problems, we actually use a chart to find the beta angle, the shock wave angle. So we discussed this, and this chart actually looks something like that. So in this is from your book as well. So in this chart, which we call as the theta beta M diagram or theta beta M plot, the x-axis is the theta angle. We started discussing this in the last few minutes of yesterday's class. So this is the theta angle. This is the deflection angle, and it's kind of given here, the theta angle. So this is a solid surface here, and theta angle is a deflection of the solid surface into a incoming supersonic flow stream. Let's say this M1 is supersonic. And the y-axis is the shock wave angle. So this is really beta that we are after. And each of these curves here, so if I can try to trace one of them, for example, this one here, each of these curves are a constant Mach number curve. Okay, so along the line that I'm drawing here right now, the Mach number is constant, and in fact, its value is written here. I will show a bigger version of it, of this. And for example, along this line, Mach number is equal to 2.2. Along this curve, Mach number is equal to 2. Along this curve, Mach number is equal to 1.6, and all that. So it goes all the way up to quite high Mach numbers. You see, for example, Mach number 20 and even infinity here, theoretical value. So this one, if you remember, actually corresponds to a certain theta max angle theoretically. So it's down here 45.5 degrees, we said yesterday. So the thing is, depending on your free stream Mach number, and if you know your theta deflection, using this chart, you can basically directly find the beta value of the shock wave, oblique shock wave, that is going to form at the corner of the deflection point. There were few issues related with this. For example, for every single Mach number curve, let's say this is Mach 1.5 curve right here, this one, there is a certain value for maximum theta. So for example, this theta is the theta max value for this Mach number. So this is 1.5. If you're flying at Mach 1.5 and somehow you have deflected some surface that is deflected higher than this angle, so if theta is greater than theta max, there is no solution to that equation. So you will not stay on this curve. If you remember, we said that that creates what we call a detached shock wave. I can try to draw maybe somewhere here. If it's a wedge problem, so if the theta and incoming supersonic flow and one greater than one, if this theta angle here, half wedge angle, is greater than theta max, we end up with a detached bow shock wave in front of it. If it's a ramp problem, so let's say we have, this could be the inlet, first ramp at the inlet of your aircraft, and one is incoming supersonic stream. This is your theta angle. If this theta angle is greater than theta max, again, you cannot have an attached shock, meaning attached to this corner. You would have a detached shock somewhere in front of this corner. Generally, we do not want, as aerospace engineers or designers, we do not want detached shocks for a reason. We will discuss about it. So generally, we need to be careful about our selection of deflection angles. At least if we would like to operate in a nominally efficient range in our normal operating conditions, we need to be careful in terms of selection of these angles. So this is how we use the theta beta m diagram. Now, another thing that we mentioned is that for a certain for a given value of theta, and let's focus on this now, Mach 2.2, you're flying at Mach 2.2, and you are flying, your theta deflection is, let's say, 20 degrees. So you draw a straight line up from 20 degrees. I guess you cut it here. So of course, the thing is, you cut the curve which is satisfying the theta beta m equation at 2 points. So you cut it here and here. The lower one happens at the lower beta angle. So somewhere here, I don't know, 45, something like that degrees. And the higher one, and the upper solution to the equation gives a much higher angle of beta, which is almost 80 degrees. Of course, since the wave angle is higher, or the shock wave angle is much higher, it's a much stronger shock wave. So that's why we call this the solution that we have at the top strong shock solution, and the solution at the bottom weak shock solution. And mostly in supersonic flow problems, we generally observe weak shock solutions. We do not observe, unless there is some strange, geometrical disturbance or something like that, we generally observe weak shock solutions. Okay, so I will show you in more detail. So these are some of the notes we already discussed. Let me see. Yes, if theta is greater than theta max, no solution. So shock is detached. for a Mach number going to infinity mathematically, or to very high Mach numbers in application, which means the theta value approaches actually 45.5 degrees. And you can actually see the Mach numbers here. These numbers. Oh, did I? Okay. Sorry. These numbers here. These numbers are Mach numbers for each curve. So you can see 2.83, 3.2, and here it goes down like that. So those are Mach number curves. So this is the other part of the graph, and we talked about weak and strong shock waves, and mostly we observe weak shock waves. And for weak shock solution, so this is another thing maybe we need to discuss. The last 2 points. So this one and this one. Now for the weak shock solution, generally, you know, here in an application like this here, M1 is greater than 1, yeah, supersonic. And generally M2 is also supersonic. M2 is greater than 1, but generally M2 is less than M1. Okay, M2 is less than M1. So basically, what the oblique shock does is actually it helps deceleration of flow a little bit. So it's not, of course, as strong as a normal shock wave, because a normal shock wave is so strong that it directly turns the flow into subsonic. If you remember, the Mach number after downstream of a normal shock wave is always subsonic. That's not the case for oblique shock waves. We generally have reduced Mach number, but still supersonic. This is quite nice because this means that, first of all, losses that are created by the shock wave will be less. Losses and the entropy generation, losses of what? For example, stagnation pressure loss. That is going to be less across an oblique shock wave, because it is weaker than a normal shock wave. So this means that instead of, for example, as we talked about aircraft inlets, intakes, for example, and we talked about the need for us to slow down the flow to a reasonably subsonic Mach numbers right in front of an aircraft engine inside the fuselage, down to the level of, I don't know, 0 0.3, 0 0.4, 0 0.5, something like that. So if the outside airflow is at Mach 2 and you need Mach 0 0.3 in front of your engine inside your aircraft, this means that basically means a significant level of deceleration. It's quite significant deceleration. And how do you decelerate? Of course, we use the physics of shock waves to do that, to decelerate the flow. And we want this deceleration to happen successively, meaning that we want this deceleration to happen through a series of shock waves, not through only one single shock wave. If you do it like that, deceleration through one normal shock wave, it would generate enormous amounts of stagnation pressure loss, which is not good for the engine inside. But instead, you can achieve the same deceleration with a series of many but weaker shock waves, most of them oblique shock waves, and one terminal normal shock wave. Then that would generate in total much less stagnation pressure loss. Well, you can ask, why are we so much concerned about stagnation pressure loss? The thing is, especially in terms of, first of all, for external aerodynamics, it means entropy generation, and it generates basically an inefficient flight condition. But more importantly, for intake design, if you remember, we talked about these ramp type intakes and generating, for example, like one oblique shock, a second oblique shock, and maybe a normal shock. So the flow gets decelerated here, and inside the aircraft fuselage, somewhere here we have the engine, right? Somewhere here we have the engine. Now the thing is, regarding the performance of the engine inside, you would like to have as high stagnation pressure as possible. So the stagnation pressure is already high outside because of high Mach numbers. You don't want to lose it a lot when because of this deceleration when you reach the face of the engine. So that's one important reason. So this inlet stagnation pressure is an important, let's say, parameter in terms of engine performance as well. So therefore, we make use of this, use of the fact that we can generate many weak shocks, a train of or series of weak shocks, and then maybe one relatively weaker normal shock wave, and then decelerate the flow. When there is no deflection, when theta equal to 0, so first of all, there is no deflection to the streamlines. Streamlines, they don't have to adjust themselves into anything. There is no deflection. So beta means the shock wave angle is either is equal to 90 degrees. So it's probably there's some kind of normal shock wave, depending on the Mach number, or there is no shock wave. So we just have the Mach wave with the angle mu, as we described yesterday. So this slide has some sketches related to what we talked about. Okay, but maybe I can say one more point. For a given supersonic flow m1 greater than 1 here, and for a given theta smaller than theta max, we have this attached oblique shock wave. And if you keep increasing this theta, you would reach a point that is not going to satisfy the theta beta m relation, and you would reach this condition, detached shock wave. And since the strength of the detached shock wave, especially in the front of this, is almost like a normal shock wave, so strength of it is going to be very high. It's going to be a very strong shock wave. Strong shock wave means lots of reduction in stagnation pressure. Okay, so that's not good. But here, that's not the case for wedge problem. And regarding the ramp flow or corner flow problem, the detached shock, as I tried to explain it here, it also gets detached from this corner and mostly acts like very close to a normal shock wave. So it also becomes very strong shock wave. So that creates lots of stagnation pressure loss, lots of entropy generation, and all that. So just two examples. Even if we are remaining within boundaries, meaning, so these are some numerical examples here. Let's say we are flying with Mach 2. So this is our flight Mach number here, and we have a wedge angle theta 20 degrees below theta max. So we don't have any detached shock wave or anything like that. We have a nice attached shock wave with a beta angle 53.3 degrees. Okay, and therefore it's okay. It's quite reasonable and nominal operating or flight condition. We can, using these angles theta, beta, and m, we can actually calculate the normal component for mn1. Let's say here, and so using this as an input to our equations, or just using normal shock wave charts, tables, or equations, we can then calculate this one as an input, using this one as an input, for example, the static pressure ratio across this oblique shock wave. Now, let's say you have this is your flight vehicle, and you cannot change the geometry, and then let's say you started to accelerate. somehow you pushed down the throttle or whatever in your aircraft, you started to fly now instead of Mach 2, Mach 5. Okay. Now the effect of this increasing Mach number, and theta is the same as you can see here. Theta did not change, still the same aircraft. Has an impact on the shock wave angle. So shock wave angle is not going to be 53.3 degrees anymore. It's going to be 29.9 degrees on the same aircraft. So it's going to be shallower, as you can see. It's going to be shallower. So, and it's actually gonna get close to the body of the aircraft, as you can see. Now, if you use these as input, so 20 degrees, 29.9 degrees for beta, and 1 equal to 5, and actually calculate the normal component, that is going to be much higher compared to the normal component here. Instead of 1.6 now, we have 2.49. Quite high normal Mach number to the oblique shock wave, which means that you will have a significantly strong shock wave, although the beta is smaller. Okay, although the beta is smaller, which means that this mn1 here is 2.49. You plug this into normal shock wave relations, that will generate a very sharp change in static pressure. In fact, the numbers are given here. If you compare them, the static pressure rise for this case will be about 7, whereas it was about 3. So so it's more than 2 times higher static pressure rise that will occur after the shock wave, and your aircraft will feel this, because your aircraft, your flight condition, whenever we are doing some calculations regarding your wings, lift generation and everything, for example, when we are trying to measure CP on your wings, CP is measured with respect to your P infinity. So if you remember CP from aerodynamics 1, pressure coefficient on your wing, for example, its definition is local pressure on the wing minus P infinity divided by the dynamic pressure square. Now this, your P infinity will be 7 times higher than your atmospheric pressure before the shock wave. So you have to take these into account. And shock wave with a shallower angle, much stronger, very strong static pressure rise. It's not calculated here, but if you calculate, for example, temperature, T2 over T1, you will see that there's very strong temperature rise and very strong density rise as well. Now, the second scenario is in this bottom row. Second scenario is, so first of all, we are flying at Mach 2. Okay, so similar to that. And initially, let's say our vehicle it has this this wedge angle at 10 degrees. And again, we do not have any detached shock wave or anything. We have an attached shock wave here. And the shock wave angle is calculated using these given values, 39.2 degrees from the theta beta M diagram. And so using the normal calculation of the normal component here gives you 1 equal to 1.26, and then that gives you, for example, a static pressure rise of 1.69. Now the thing is, if we keep Mach number the same, okay, so Mach number is kept the same, and basically what we are changing is angle theta. So nothing, we are just changing the geometry. Somehow, let's say we have some transformable geometry, we increase the angle 2 times. Instead of 10 degrees, we changed it to 20 degrees, which automatically changed our beta angle to 53 degrees, which automatically changed our normal Mach number to 1.6. and the static pressure rise to 2.8. So you see 2 times increase in theta. So keeping everything constant, meaning flight Mach number M1 constant, but increase in 2 times increase in the theta angle or the geometrical angle resulted in a rise in static pressure from almost 1.7 to 2.8, which is less than 2 times. Okay, and also if we take a look here, although beta angle is higher, it's still I mean, in this case, it becomes a little bit stronger shock wave than the first case here because the static pressure rise. I mean, first of all, I need to maybe clear this up. When we talk about strong shock wave or weak shock wave, we refer basically to the static pressure rise. Generally, when we say normal, I mean, we refer to a few things. A strong shock wave has big static pressure rise. A strong shock wave has big reduction in Mach number, and a strong shock wave has big reduction in stagnation pressure. Okay, if we are talking about the weak shock, small rise in static pressure, small rise in static temperature, small reduction in Mach number, and also small reduction in stagnation pressure. Okay, I just got a phone call. I need to take this, so I will pause the recording for about 2 to 3 minutes, and then I will be back. Okay, I just need to take this. So let's give it like a 3-minute break, and then I will be back.
Hocam,
Okay. Evet.
May I ask a question about these
Mm-hmm.
oblique shock waves?
Mm-hmm.
Hocam, in some cases, like next generation fighter aircrafts, it is desired to have declined surfaces to avoid some
Mm-hmm.
interactions with electromagnetic and sound
Mm-hmm.
waves
Mm-hmm.
to detection of to
Mm-hmm.
overcome the detection of aircraft.
Right.
In these cases, do we still obey the rules about oblique shock waves that we need to have attached oblique shock waves to have more desired flow
Mm-hmm.
around the body, or do sometimes we have a detached flow over these surfaces?
I mean, regarding radar signature and regarding the shape of this aircraft, normally, I mean, the thing is, you need to do something to deflect the electromagnetic waves, right? And to deflect the electromagnetic waves, I mean, one option is to use, give angles to the surfaces like that. Okay. So instead of making a surface, flat like that, you have to give angles to reflect electromagnetic waves to different directions, so that you will reduce visibility on the radar. So this was first tried in F-117. Okay, that was the first one of the first fighter aircraft that used this, and I don't know if you remember its shape, but it's all triangles all over it. Okay, but and it did have radar problems, but it was basically mostly flying subsonically. Okay, now of course this was early 80s development, 1980s. Modern aircraft they do have stealth capabilities, still have this thing, but since we can design in a much better way, our computers are stronger, we can achieve this in a much, let's say, we can give these angles in a much smaller fashion, smaller variations. So from outside, it basically looks like a straight line, or just like a curved line, but in fact it has little minute deflections that deflects off the radar waves, electromagnetic waves. So overall, shock wave So it's better suited for shock wave generation and supersonic flight. So for modern aircraft like F-22, F-35, the fifth generation, I must say, fifth generation fighter aircraft, it's mostly like that. The Sukhoi 57, it's they do have stealth capability, but they are also aerodynamic in shape. Okay, and if so, any everything that we discussed so far regarding whether it's going to be attached or detached shock waves, of course, it's valid for anything that is flying supersonically. Okay.
Teşekkür ederim hocam.
Yes. So let me turn off this PowerPoint, and there's another one. I will continue if because we have only 10 minutes. I will continue about this next week, but okay, so let's start from this slide here.
Hocam,
Another
also,
question.
is it possible to share this slide with us if it's no problem to Uğur Hoca either?
It's going to be in the video anyway, but I have to check with Uğur Hoca and Mustafa Hoca.
Teşekkür ederim hocam.
Now we talked about total pressure ratio, but anyway, let's this kind of summarizes it. The thing is, for example, so again regarding aircraft intake. So this is let's say an intake here. So somewhere over here you could have your engine buried inside the aircraft, which is expecting a subsonic inflow condition, and not only subsonic, mid-range or low subsonic condition, 0.3 to 0.5 Mach number. So you could achieve this only through a normal shock wave, as it's shown here. Okay, you are flying supersonically. If you design this shape properly, you could only generate one normal shock wave, and then right behind it, you would definitely have, because it is a normal shock wave, you would definitely have a subsonic Mach number, and then you can do other tricks and then slow it down to required inflow Mach number. This is one option. You can do that, but the total pressure loss, especially if this Mach number is significantly high, I mean, the aircraft is, let's say, if it's a low, let's say low supersonic flying aircraft, so maybe a design Mach number of 1.2, 1.3, so low supersonic flying aircraft, this wouldn't be a big issue. In fact, there are aircraft like this. For example, you can check older generation fighter aircraft like F-100, for example, or F-86. These older US-built aircraft, there are counterparts of this aircraft, Soviet-built aircraft as well. They have exactly, in fact, this is the nose of the aircraft. For example, in F-100 and F-86, nose looks exactly like this, but during it, of course, it has very limited supersonic flight capability. It can fly for a limited time only at low supersonic speeds. Then in that case, basically what happens is there is either a normal shock wave, a little bit detached, or a normal shock wave attached, but just sitting somewhere here, right at the front of the aircraft. So since infinity is not that high, so with reasonable pressure, reasonable amount of reduction in pressure, you can generate a subsonic flow into the engine. That's not the case if you start flying at higher and higher Mach numbers. So Mach 1.5 and above, that's not a good idea to use a single normal shock wave to decelerate the flow. Instead of that, we use, as we discussed, a series of shock waves. So this is one simple example. We have only, in reality, one oblique shock wave here, and generally we could have more than one, and one normal shock wave, which is I mean, the thing is, what happens in reality is this infinity, or let's say M1, is supersonic, but it gets to reduce a low supersonic value after the first oblique shock wave. If there are more oblique shock waves, it gets even reduced further, but still to further low supersonic values. So when when the flow reaches right upstream of the normal shock wave, right in front of it, the Mach number will be barely above supersonic. So this normal shock wave will be very weak. So you will have a reasonable, very, very low pressure loss and then go to subsonic right after it. And then very large area increase makes it go to even much lower levels in subsonic speed. So the engine will be happy. So depending on the number of ramps here, or depending on this design, this shape, you could have one or more oblique shock waves in front of the normal, what we call terminal shock wave, which means final normal shock wave. We say it's terminal because after this it becomes subsonic. Before that, in front of this normal shock wave, however number of oblique shocks you may have, it's always supersonic. In many aircraft, and I think we watched this in the video a few weeks ago. For example, the inlet for SR-71 aircraft. You can watch that again if you want, or you can look it up in YouTube. SR-71 and like MiG-21, all these aircraft they have an inlet which looks very much similar to like this. And in reality, this piece here is movable in those aircraft. It can move back and forth. It can move back and forth. So basically, the purpose of this is that depending on your flight Mach number, it can move back or move forward so that it will always keep the shock wave attached to here, to this point here, and to this point here. Okay. If the shock wave is not attached to these 2 points, maybe, for example, if it's like that, it's also an inefficient design and inefficient condition. Or if it's too shallow, it goes inside the intake, which is also inefficient condition. So in nominal design operating condition, you would want this oblique shock wave attached to here and to the lip, what we call the lip of the intake. So, so in order, and as you know, as Mach number M infinity or M1 changes, since theta is constant, beta will be different. So shock wave angle will be different. So in order to manage that changing beta angle, we move this back and forth in those aircraft. There are nice animations and videos about this. And it's, as I said also yesterday, in propulsion 2 classes, normally, I think these must be taught. It's a part of propulsion 2, aircraft engine intake design, subsonic intakes, supersonic intakes, multiple oblique shock intake designs, all that. So another issue, let's quickly discuss this, then we will finish up for today. The flow over a wedge and flow over a cone. So in here we have 2 cases. We have a wedge on the left and the cone on the right with the same incoming Mach number, Mach 2, and same half angle, 20 degrees theta angle in both cases. But there's a geometrical difference. A wedge, so it's the cross sections of both of these shapes, a wedge and a cone, they both look like a triangle, right? So this is a triangle, this is a triangle. But the cross section might look the same, but the geometry is different. So in 3 dimensions, for example, a wedge, when we say wedge, we understand something like that, like more like a 2-dimensional shape, something like that. Okay, something like that. But a cone is a cone. A cone does not look like that. You know how a cone looks like. So in the case of a wedge, and given M1 and theta conditions, it's basically more or less it creates a more or less a two-dimensional flow. So the streamlines are directed parallel to the surface at 20 degrees, and the corresponding beta angle can be determined from the theta beta m diagrams. So everything that we learned so far is valid. But if it's a cone is has a more complicated flow physics, meaning that first of all, it's a three-dimensional shape, okay, and it's the flow around, so that makes the flow around it three-dimensional. And basically what happens inside a cone is, for example, this surface is at 20 degrees, right? But if you draw another line inside a cone, for example, at a lower radius, that is not going to be 20 degrees. If you draw another line inside at a smaller radius, that is not even small, or going to be even smaller than that angle. So that kind of variation gets reflected on the streamlines as well. The streamlines, as you go away from the cone, each of them will be deflected at a different angle. That's not the case for the wedge. In the wedge case, every streamline above the surface are exactly deflected at 20 degrees, which is this angle. Not the case for cone. Every streamline will be deflected at a different angle, but the shock wave angle will be constant. So shock wave angle is constant. However, streamline angles will be different. But another thing, important issue is that because of the three-dimensionality of the flow, the shock wave angle for the cone case, although the Mach number is the same, the maximum angle, this is theta 20 degrees, is the same, is less than what you would have in a wedge problem. Okay, so it is a little bit out of context of this class because it's a three-dimensional flow effect, and these are a little bit more advanced topic. But just to keep in mind that these two things are not similar. They do not have similar flow physics. In fact, a little bit less beta means a little bit weaker shock wave in the case of a cone, and give for the same inlet conditions, for the same Mach 1 is equal to 2 inlet conditions. Okay. Anyway, so we have few more topics that we will cover, like shock interactions, again related to intake design and shock reflections, but that will come. We will talk about it starting on Wednesday next week. Okay, so let's stop here. And if you have any questions, I can try to answer. Okay.
Daha sonraki dersleri slide üzerinden mi işleyeceğiz?
Yok, burada bazı figürler olduğu için, onları kullanmak istediğim için slide üzerinden gittim, ama slide
Tamam
veya video veya whiteboard, hepsi hangisi uygunsa oradan gideceğiz.
Teşekkürler.
Tamamdır. Peki, o zaman haftaya görüşürüz. Stay safe, take care of yourselves. Talk to you next week.
İyi günler hocam. Dikkat edin kendinize.
İyi günler, aynen siz de. Hoşça kalın.